In this video, we'll discuss multiple linear regression. To start, we're going to need to talk about functions of several variables. So from past math, we know that a function just assigns an input x to an output y. Usually we write this as f of x equals y, or x with that arrow there to y. We actually say that x is mapped by f to y. Now, as a part of a function, every x must get a value y, but not every y must be assigned to for some particular x. So that's the function criterion that you probably learned somewhere in the past as the so-called vertical line test. These are so-called univariate functions. They have one input x and they have one output value y. Multiple regression, by contrast, uses multivariate functions. A multivariate function is a function of more than one input. So if there's two, it would look like this. F of x1, x2 equals y, or sometimes we would say the pair x1, x2 gets mapped to y. Or sometimes if we don't want to use x1 and x2, we would say f of xy equals z, and that would be fine as well. In this context, every pair x1, x2 gets a y. This kind of function in this case is said to be bivariate because it takes in two inputs and it returns one output. If it were to take in three inputs, we would call it trivariate, and in general, we refer to all of these as just multivariate functions, or functions of several variables. Now, as far as graphing goes, when we graph a univariate function f of x, we get a curve back. The graph of the univariate function, the curve itself, is like a one-dimensional object in two dimensions. What I mean by one-dimensional object is it's like taking a line and then pushing parts of the line up or down, okay? I can't have the line curve around like a circle because that would violate that vertical line test, but I can move it up and down, and in fact, I can even tear it, and I would still get a so-called curve back, at least for this sense. More formally, the graph of a function is the set of points x f of x. In this case, it's a univariate function, so there's one x, and f of x is y, so this is just a whole bunch of points in the plane. As an example, consider the function y equals f of x equals the sine of x plotted between 0 and 2 pi. That is the curve that looks like this. Every point on that curve is one of these pairs x f of x for some x. Now, what happens when we graph bivariate functions? When we graph bivariate functions, we get surfaces. So if univariate functions are curves, bivariate functions are surfaces. Surfaces are two-dimensional objects in three dimensions, and this is usually described as something like a sheet. You can imagine a bed sheet. If you picked it up and just kind of waved it, that would be the shape of a surface in three-dimensional space. More formally, of course, the graph is actually a set of points, x1, x2, and then f of x1, x2. Now notice that in this case, we will denote the pair of inputs as bold x right here. Notice that that's a little bit more bold than the other x's, and then with the y here in the end. So if there are, say, two x's, x1, x2, this object is going to be an R3, where it's going to have three real numbers associated with it, and those are x1, x2, and y, okay? That's what the graph will look like. It's those set of points in three dimensions. As an example, take now the function y equals f of x1, x2, which is equal to sine of x1 plus a sine of x2. Of course, just to evaluate that, somebody gives you an x1 and they give you an x2. You plug those numbers into the sine function, and then you add the outputs. If we were to actually graph this, we would see this sheet in three dimensions that looks like this, which is kind of like a multivariate sinusoid. Now, graphing in three dimensions tends to be challenging, and it introduces perspectival problems. So usually you only want to graph in three dimensions when the user has the ability to rotate the graph around. To get around this problem, what we often do is to project the entire surface down into the xy plane and then color that sheet by what were the heights before it was projected. And we get something like a contour plot. So contour plots are kinds of surface plots, but they're actually shown in two dimensions, even though you're seeing an object in a three-dimensional space. So you're seeing a higher dimensional object in two dimensions here. They're just not spatial dimensions. Instead of contour plots, you can imagine having a whole bunch of these slices, kind of the number of slices goes to infinity, and you get something that looks like this, which is probably a little bit better of a plot, even though it's a little bit more difficult to interpret, because different shades of the colors are difficult to actually see, but these would be called density plots. Notice, of course, that density plot is very different than the kernel density estimator that we would get with something like geom density. In general, ggplot2 will not make any kinds of three-dimensional graphics using three spatial dimensions. However, you can achieve three-dimensional graphics using other aesthetics, like shape or color or size. If graphs of bivariate functions f of x1, x2 are surfaces, graphs of multivariate functions in general are called hypersurfaces. For example, if you were to take in an x1, x2, x3, the return value would be y. That would actually need to be a three-dimensional object in 4 dimensions. But of course, we can't see in 4 spatial dimensions, so hypersurfaces in general are very hard to visualize. Nevertheless, mathematicians have studied these kinds of objects and their shapes for centuries at this point. This is the field we know as geometry. As an example, you'll undoubtedly be familiar with Einstein's concept of space-time as having some kind of shape and being curved by massive objects like stars or black holes. And because of this, you'll see pictures that look like this for the curvature of space-time. Of course, this picture is not an adequate representation. It's trying to show something that is in a higher dimensional space that's being bent in that higher dimensional space, but we don't have the ability to see it in a lower dimensional space. Okay? Now, let's talk about some special cases. Planes and polynomials. Lines are the graphs of polynomials with degree 1. So we said lines are equal to beta naught plus beta 1 times x. That's a polynomial, and the power on the x there is 1. Okay? If we had a multivariate polynomial, that is to say a polynomial that has more than one input variable, it may look something like this. Y equals f of x1, x2 equals beta naught plus beta 1, x1 plus beta 2, x2. And the graph of that would be a plane in 3 dimensions. So a 2-dimensional plane in 3 dimensions that's just not lying flat. Or maybe it is lying flat if beta 1 or beta 2 are both 0. In a higher dimensional space, we could get a hyperplane by looking at the graph of a polynomial that's of degree 1 and it's in several variables. So instead of just being in 2, which we get a plane, or 1, where we get a line, we could have several variables and we get a hyperplane up in some higher dimensional space that we cannot visualize but nevertheless is there. These are all degree 1 polynomials in the sense that the sum of the powers in each of the terms is 1. In fact, if we look at each of the terms and we look at the x, there's only one x and its power is at most 1. Of course, for the beta naught term, its power is 0. In all of these cases, the interpretation of the betas is the same. A 1-unit increase in xi, that's the ith variable that we're looking at, results in a beta I increase in y. And that's pretty easy to see using the same math that we used before to see that result. Moreover, if we set all of the x's to 0, beta naught is interpreted as the intercept, just like it was in the previous scenarios. Interpretations of other polynomials is more complicated, just in the same way that it's more complicated in the univariate case. So if I have a polynomial beta naught plus beta 1x plus beta 2x squared, we know that the interpretation of that is going to be a little bit different than if it's just the linear interpretation, because the linear interpretation will hold globally, regardless of whatever the x is. If you increase the unit of x by 1, you get a constant change in y back. But if you have, say, a square in the x, now that unit 1 increase is going to effectuate a different change depending on where you are on the x-axis. What would that look like in the bivariate setting? It would look something like this. Y equals f of x1, x2 equals beta naught plus beta 1, x1 plus beta 2, x2 plus beta 1, 2, x1, x2. That last term is referred to as an interaction term between x1 and x2. Notice that if both x1 and x2 are positive, or if both of those are negative, the resulting product, x1 times x2, is going to be positive. And if they're opposite signed, it's going to be negative. These interaction terms are usually thought of as having some joint effect, and the interaction term itself in that product is what's actually mathematically manifesting as that joint effect. The interpretation of the betas, of course, is no longer global, as it will depend on the other x's. Notice that the degree of that polynomial is actually degree 2, because in the last term it has powers on x1 and x2 both equal to 1, and when you add them together you get a power equal to 2. So it's very much like a quadratic, just like in the univariate setting. So that's the background math here. From there, multiple regression is actually very easy. Usually we want to predict a y, a response, with more than one predictor. In almost every scenario, we have more than one predictor that actually says something about our response. As a basic example, we could have something like an individual's weight could be dependent on not only their height, but also their age, or maybe other factors as well. That would be a scenario for multiple regression. Or in the context of water, maybe we have the water's pH is dependent on the dissolved oxygen and the depth. So not only are we going to take into account the dissolved oxygen content of the water, but we'll also look at how deep is that water when we're trying to predict what is the pH of that water. The data set would look something like this in general. Usually we think of the number of x's we have as being p, so we would say we have p predictors, and the data would just be a collection of n observations The first p numbers of those would be x1 through xp, and then the last one would be yi. Obviously, as you go into higher dimensions here, the notation just gets a little bit more complex on us. We have better ways of dealing with this in more advanced statistics classes, but for here, this will do us just fine. Usually we'll lump together all of the x's as one vector, and we'll boldface that vector like that, so that we usually still think of these as pairs, but the first element of that pair is actually a vector that contains several different measurements. And of course, the sample size is still n, and the data structure in R would also be a tibble or a data frame. In terms of the nomenclature, when we have one predictor and one response, that's called simple linear regression, and the resulting kind of object that you're looking for is the best fit line. That's the resulting geometry. It could be a parabola or some other shape, but it's a best fit curve. In multiple dimensions, we have multiple regression, or multiple linear regression. We could call this MLR, and we get a best fit plane if the polynomial is a degree 1 polynomial, and if it's not, we get some other kind of geometry. Either it's a sheet or a trough or something like that, just depending on whatever the graph of that function looks like. Now, this is a situation where our math really helps us out. If you're trying to just eyeball a relationship between two variables, x and y, you may have actually asked yourself the question, well, why do I need all this math? I can actually just draw a best fit line between among my points x, y, to come up with a prediction mechanism. And that's absolutely true. The problem comes in generalizing that into multiple dimensions. So it's very difficult to draw, for example, a best fit plane or a best fit hyperplane, which is essentially not even possible. So mathematizing this scenario is actually helping us out here because it's going to generalize, or it's going to allow us to generalize things very well. This is where models help because we don't have the ability to visualize things. Now, fortunately, everything in multiple regression essentially generalizes directly from simple linear regression. For example, the best fit criterion that we gave before about minimizing the residual sums of squares, that's just as true now as it was then. If the functional form f of x is linear, it has the exact same interpretations, just like we described in terms of planes and hyperplanes a moment ago. Prediction is done in precisely the same way. If you have a new x value, a new x value in this case, of course, would be a vector of values. It would actually have several different measurements associated with it. For example, the height of the person and their age. You would plug it into your model and you would get a number back that would be your y hat, and that's what you would use for prediction.